In the last video, we looked at some foundations of survey design for spatial capture-recapture. In this video, we look at some example designs and try and pick out good and bad aspects of each. To recap, our overall goal is to come up with a design that estimates abundance or density precisely and without bias. We saw how a good way to go about doing this is to try and find a design that detects many unique animals, gets a lot of recaptures, gets those recaptures at a variety of distances, and also avoid sampling good or bad habitats preferentially. To look at some example designs, we'll focus in on the survey region, just south of Bishkek in Kyrgyzstan. The survey area is about 13,000 square kilometers, and so it's a lot bigger than what you typically survey with a single camera trap array. Nevertheless, it'll let us discuss some of the principles behind good and bad survey design. To begin, let's zoom in on the survey area and divide it up into a number of grid cells. Here, each grid cell is 1.5 square kilometers, although the exact size of the grid cell isn't critical. What's really important is just that we've taken the whole survey area and divided it up into grid cells. Micro-level survey design will only tell us which cells we should visit. The decision about where to place each camera within each selected cell gets left up to the researcher. Here, a good guideline is that if there's a snow leopard within a cell, we really want to detect it. So this means placing cameras in the best possible spots within each selected cell. We'll start off by assuming that we know nothing else about the survey region, so we've got no covariance information, and we're assuming that animal density is constant throughout the region. Now let's look at a few designs. In this design, cameras have been spaced 25 kilometers apart. When thinking about spacing between cameras, it's really useful to think in terms of animal home ranges. Here, in blue, I've plotted an approximate 99% home range based on an estimate of sigma of 4 kilometers. The size of a home range gives you a rough idea of how far an animal will move. By looking at the spacing between cameras and the size of a home range, here it's immediately clear that it's going to be very difficult to detect an animal across more than one camera. In other words, with this design, we're really going to struggle to get recaptures. The problem with this design is that cameras have been placed too far apart. With this design, we've got the opposite problem. Here, cameras have been placed very close together. Putting cameras close together is good for recaptures because if an animal is seen on one camera, it's likely to be seen on another camera. But in this case, this design has got two problems. The first is, because we've put cameras really close together, the camera trap array covers a very small area. And so unless animal density is really high, we're probably only going to detect one or two animals. Secondly, although we might be getting a reasonable number of recaptures, those recaptures won't be at different distances. To see this, think of an animal with an activity center over here. We might detect it on a camera and several other nearby cameras, but all of these cameras are separated by a very small distance. That means that we're only gathering information about a very small part of the detection function. This will lead to high variance in estimates of sigma, and these will spill over into imprecise density estimates. So another failing of this design is that we're not getting recaptures at different distances, even though we might be getting enough recaptures. In this design, we've struck a balance between the previous two. Cameras are spaced 6 kilometers apart, which is 1.5 sigma. The array covers a full home range, so if we get recaptures, we're likely to get these at a range of different distances, and this is good for estimating the parameters of the detection function. Nevertheless, there are some concerns with this design. The first is that we're not covering a very big area with the array, so if animal density isn't high, we might not detect very many unique animals. Also, if encounter rates aren't high, we may not get very many recaptures. It's hard to say for sure if this is a bad or a good design. We've done about as well as we can with choosing the spacing between cameras, but we might just have too few cameras to detect a reasonable number of animals and recaptures, so there are question marks about the first two of these. In this design, we've used clusters of detectors. Each cluster consists of 4 detectors placed very close together, and there's a substantial distance between clusters. Cluster designs are a good way to cover a bigger survey area and so detect more unique animals, but still retain a reasonable number of recaptures by putting some detectors close together. The problem with this design is that we've put the cameras in each cluster too close together, so we're going to have the same problem as when we put cameras too close together. If an animal has got an activity center here, if it's detected on one camera, it will probably be detected on others, but this gives us very little information about sigma. So, although we're covering a large area and so we should get a reasonable number of unique animals, and we've got cameras spaced close together to get recaptures, those recaptures won't be at a variety of distances. With this design, we've tried to increase our number of captures and recaptures by increasing the number of cameras. It's hard to say for sure, but this is probably a pretty good design. Our array covers a reasonable area, so we should detect a reasonable number of unique animals. The spacing between detectors is small enough to encourage recaptures, and the fact that we cover a couple of home ranges mean that those recaptures should be at different distances. Because we've placed our grid randomly in an area where we're assuming constant density, there's little danger of bias. Here's another design that's probably fine. Here we're using two clusters of detectors, but each cluster is at least as big as a home range, so we're detecting recaptures across a range of distances. All the designs we've looked at so far have been regular grids, but this doesn't have to be the case. Here's a design that's probably also good enough. It's covering a reasonable sized survey area, and the spacing between detectors is small enough and varied enough to get recaptures at a variety of distances. Up until now, we've assumed that density is constant throughout the survey region, but what happens if we want to model density as dependence on a covariate, for example ruggedness? Here I've indicated rugged areas in light blue and less rugged areas in dark blue. If we want to model density as depending on ruggedness, we need to make sure that we sample the covariate space well. That's to say, we need to place some cameras in rugged areas and some cameras in less rugged areas. A design like this is fine because it does that. The cameras towards the south are in rugged areas and the cameras towards the north are in less rugged areas. We've sampled a range of covariate values, and so we'll be able to estimate the relationship between density and ruggedness well. In contrast, here we've only sampled rugged areas, and so we won't be able to estimate that relationship well. This may land up biasing our density estimates. So to summarize where we are, our overall survey goal is to estimate abundance precisely and without bias. We've looked at a 4-point checklist that tells us the kinds of things that we need to achieve this goal. We need to detect enough unique animals, we need to detect enough recaptures, we need those recaptures to be at various distances from animals' activity center. We also need to avoid oversampling good or bad habitat because this could lead to bias. Standard guidance on camera trap survey design suggests that cameras should be spaced between 1 and 2 sigma apart. For snow leopards, it's often really difficult to get recaptures, and so it's reasonable to space some pairs of detectors closer than 1 sigma, but this should be the exception rather than the rule. Together, the camera trap array should cover, as a bare minimum, 1 home range, and preferably more than this. If you're going to model density as a function of covariates, you need to make sure that your cameras sample a range of high and low values of that covariate. In this video, we've tried to get an intuitive feel for this 4-point checklist, but the good news is that each of the items on it can be checked beforehand using simulation and numerical calculations. We'll see how to do that in the next video. We looked at designs suffering from 5 common pitfalls. Cameras could be too far apart, too close together, there could be too few cameras. Where we used clustered designs, the clusters of detectors could cover too small an area, and we could oversample good or bad habitat. Each of these pitfalls leads to a failure of at least one item on the 4-point checklist. In the next video, we'll look at some software that can help you take a possible design and make sure that it's got the good properties on the 4-point checklist and avoids the pitfalls.